All right, the last review of the year, the last unit of chemistry, and that pretty much takes us to the end of the semester. And I know I've said this for the other ones, but I'm hoping this will be a little bit shorter because a lot of the homework questions, homework sets, they're just really repetitive. I gave you a lot of examples. There's going to be a lot of balancing here, for example, and then some identifying of shapes of molecules and being able to draw Lewis structures, or for the final, because it's multiple choice, just identifying what's the correct Lewis structure, for example. So let's go ahead and I'll just start with, like I did last time, with reviewing this what you need to know sheets from this. And let's go kind of line by line. So yes, you should write down those because those are the prefixes that we use for molecules, covalently bonded compounds, nonmetals bonded to nonmetals. So you'll have to know those. Yeah, you should know the diatomics. The polyatomics, remember, we're going to have those in the solubility table, so you don't need to memorize those or even write them down. Just remember that they are in the solubility table. You still should know the names of those. And of course, any chemist should know all of those things there. Know endothermic and exothermic, and then be able to give the names of the 8 shapes I made you responsible for. And I won't ask you about the angles. I should have, but I, for some reason, said I wouldn't make you, so I'm not going to change my mind now. We already talked about this before in the last unit, so still be able to tell the difference between an ionic and a molecular compound based on the formula. Again, if it's just nonmetals, it's molecular. If it has a metal and a nonmetal, or you see a polyatomic ion, it is ionic. And the ones that are molecular have covalent bonds. The ones that are ionic have ionic bonds. Kind of going this a little bit quickly. Like I said, there's not a lot. We just did a lot of practice. And in fact, just kind of stopping before we get to the balancing over here. This year, I did something different is when I first introduced the types of reactions and balancing, I always just gave you the products and you just had to add coefficients. I think it really helped people this year. And then later on, I made you responsible for coming up with the products yourself. And I think that worked out well. So that's what I'll do also on these, going over these homeworks, is that I'll first just do the initial style of just providing the products and you just balancing it. And then later in the homeworks, we'll go over ones where you have to come up with the products yourself. Anyways, back to our little story there. Chemical formulas and naming compounds. So you had already done in the previous units how to name ionic compounds, but I gave you a little reminder here about how to do that. But the new thing is how to name molecular compounds. So I won't go over the rules there. Just when I start doing problems, I'll kind of stop and remind you how to do those. So make sure you know how to do both. Write down the rules on your cheat sheet if you don't think you'll remember, or you need just a little bit of help during the final. And then balancing, there's not much to say there. Is that you just add coefficients. Once you have all the reactants and products, you're just adding coefficients to balance it. So you have the same number of each element on both sides of the arrows. And then remember that whenever you have one of those Brinkelhoff elements, when it's by itself, you write it as something 2. So Br2, I2, N2, etc. If it's part of a compound, it could have any subscript. But when it's by itself, a diatomic element has a 2. Then types of reactions. So remember, again, we do the homework, we'll go over this. We have synthesis, decomposition, combustion, single replacement, and double replacement. And kind of know how we're going to balance those when we have to come up with the products ourselves. And remember that combustion technically means just that it's reacting with O2 gas. But the one that we practice a lot is when a hydrocarbon combusts, it reacts with O2, but the products will be CO2 and H2O. You have to know that. And so I think I'll just skip those. These here, I think I spent a lot of time on the previous 2 video reviews going over this summary sheet, and then it just got kind of long. I'm going to give you plenty of examples when we go over the homework here. I'll just leave these for you to do yourself. The next sheet, I don't know if I put it here. Did I put it here? Yeah, I put the answers there. So I'll just give you some extra problems to do. So I'll just skip those for now, but know how to do those problems, okay? Then we did stoichiometry, and I'm trying to remember. I guess this is the unit that I did all of stoichiometry. I don't think I started the last unit. So it's that whole idea about if I tell you how much you have of each product, figuring out how much of each reactant, how much product you'll form, including when I said we had limiting reactants. Again, I won't do this one. I'll leave you to do these if you want, and check your answers down here. But I'll just do some on the homework, again, for the sake of hurrying a little bit. Then we learned a little bit about thermodynamics, the difference between exo and endo. And again, I'll wait till we do the homework questions to go over those. So this is just a reminder of what you need to know. And then I'm not going to do much about the shell model. It was just a way, I'm going to kind of cross it out. I typically don't in a chemistry course. It's kind of just that vague kind of idea that how many electrons can fit in a shell. But in real chemistry, you learn all the subshells and orbitals and stuff like that. So I usually don't spend much time on that. I'm not going to have you draw that. As I'm saying here, we quickly moved away from that generic shell model. But be able to know how many valence electrons something has. Pretty easy. We'll do a question like that. Know your trends for atomic radius, i.e., EA. And later on, I'm not sure where I put that, electronegativity. It's probably somewhere in the next section or something. But know those trends, and we'll go over that. And I don't think I'm going to ask you any explanation questions. It could be that I do ask you an explanation question in the form of a multiple choice question. Like I could say, which of the following statements will explain why the radius decreases as you go left to right or something, and hopefully you'll recognize the answer. But leaning towards not doing any of that, but I wouldn't bother writing them. I think you understood the explanations. Understand what ionization energy means in terms of, does that mean it's easy to form a positive ion, or is it hard to form a positive ion? Same idea with electron affinity. Understand what a high or low electron affinity mean. Now, Lewis dot diagrams, again, you don't have to draw them. This is multiple choice, but you should be able to identify whether something is the correct Lewis dot diagram based on drawings that I provide you on the question. So and we'll go over these on the homework. Again, I'm hurrying through this review sheet. We did Lewis dot diagrams for just single atoms or monatomic ions. I could ask that. I'm not sure if I'm going to waste a question on that. But then we started doing them for ionic compounds. And maybe that'll be on the final. The bigger use of Lewis dot diagrams are for molecules, not ionic compounds. But I will go over on the homework an example of a Lewis dot diagram of an ionic compound. And again, I'll let you do this one on your own as you're studying, or you can look at the answer key below. But yeah, then we moved to Lewis dot diagrams for molecules involving covalent bonds. So know this idea that, this octet rule, which really isn't a rule, it's a tendency, that we're always trying to give 8 electrons around things. But I wrote some things here that, and this kind of gave you the idea of how you do the pro mode that I called it. But you don't need to memorize these. You could write them down. But generally, some of the hints that we know if we're on the right track are those second period nonmetals, C, N, O, and F, will always follow the octet rule. They won't have fewer than, unless it's kind of a weird exception. But the ones I'll give you, they'll have 8 electrons around it, not 6, not 10. Then the special ones, hydrogen only wants 2 electrons, in other words, a bond and no lone pairs. Beryllium actually only wants 4 electrons. It'll have 2 bonds and no lone pairs. Boron only wants 6. It'll have 3 bonds and no lone pairs. And the nonmetals below the second period, so third period or lower, they could have more than 8 electrons. We call them expanded octets, which is a contradiction in terms, kind of. Especially we see that for phosphorus and sulfur. And the halogens, when they're terminal atoms, don't give them a double bond or triple bond. They're too greedy. If a halogen is a central atom, yes, then it could be forming multiple bonds, but as a central atom, as a terminal atom, it will just be a single bond. I kind of lied. Let's go ahead and do this one just for a little practice. I think we're not going to do this one. So just for a little practice, how we do this is we count up the valence electrons. Sorry, the pen. So nitrogen has 5 valence electrons. Each oxygen has 6. But since it's a negative ion, we need to add one more. It has an extra electron. So that's 18 electrons, right? Or 9 pairs. So again, how you do this is I'll tell you what the essential atom is, and we make our bonds first. That's the first thing we have to do. That's 2 of our 9 pairs. And now with leftover pairs, your first goal is to give the terminal atoms an octet unless it's a hydrogen, which doesn't want any lone pairs. So we're at 2, we've got to get to 9. 3, 4, 5, 6, 7, 8. Now, we got to stop there. We gave all the oxygens an octet, but we have 1 left over. Where does it go? It goes on the central atom. But there's one more thing you have to do. What is that? It's a polyatomic ion, so you put it in brackets and put the charge on the outside. These should become really easy. It seemed really easy, and there's a reason why I knew I wanted to do an O2, because there's one other thing we needed to do. Before you box your answer and move on, we need to check to see if the central atom is happy. So how many electrons does the central nitrogen have? 6, right? So what do we do if we have a central atom missing 8, not having 8, having fewer than 8? We take a lone pair from a terminal atom, take that one for example, and we'll move it to become a double bond. And now that oxygen still has 8 electrons, but now that nitrogen has 8 around it too. So always do that. Check to see if your central atom has 8. If not, move a terminal lone pair from a terminal atom to be a lone pair. The only time you won't do that is if beryllium were your central atom. It doesn't want 8, so don't make a double bond if beryllium only has 4 electrons around it. It only wants 4. And if boron's the central atom and it only has 6 around it, well, don't make a double bond. Boron wants 6, it doesn't want 8. Okay, almost done here. So VSEPR, you have to know the names of the shapes. You won't have to draw them, but if I give you a drawing of a shape, you should be able to identify what the name of that shape is. So again, we'll go over this, actually below this page, some of the review of this. And what I'll explain later is I'm more likely to ask you the name of a shape based on the Lewis drawing, for example, this, rather than me doing that sort of 3D shape. I'll explain what I mean when we get to the next page. And then the last topic is polarity. There's a lot of explanation there, but once we understood, there's electronegativity. Understand what electronegativity is and what the trend is. It has the same trend as IE and EA. And then I kind of mentioned how you could find whether it's polar or not, but it came down to kind of memorizing these rules, which maybe I'll summarize a little bit later, but I'll go ahead and, since I summarized it here, I'll go ahead and say it verbally. So if you have one of our 5 original shapes, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, if all the terminal atoms are identical, it's nonpolar, guaranteed. The ones that we're going to say are going to be polar, guaranteed, are the 3 that we learned that have a lone pair on the central atom. Now again, when you get to 10th grade chemistry, you're going to see there are exceptions where some shapes that have a lone pair on the central atom can be nonpolar. But for the 3 that we learned, the 2 bent shapes and the trigonal pyramidal, those are automatically polar for our class. The other thing that will be quote unquote automatically polar is anytime that the terminal atoms are different. But as we did in class and we did on homework and even I think the test, there could be an arrangement of the atoms, if they're different, the terminal atoms, where it ends up being nonpolar. Okay, and then unfortunately we didn't get to that. That was kind of our last topic. Again, we lost out a bit because of ISAS and the storm at the beginning of the semester. So here's what I was mentioning is I provided these, so know what these shapes are called. I don't know why I did this, but you don't need to know their angles, okay? But you should know all these shapes that I gave you. I crossed out the ones that you'll learn in chemistry in 10th grade that I'm not going to make you responsible for. I don't know why. Again, I think you guys are good at this, just to save a little time, I think. I'll probably take another half a day or so to go over those. And a lot more problems that I'd have to give you to practice. So, anyways, I'm going to show you a different method, not a different method, but a different representation. But I mean, you can kind of see the shape here. That's trigonal planar. That is bent, because we don't think of the lone pair when we're naming the shape. The shape is based on the arrangement of the atoms, not the arrangement of the regions of electron density. And again, that's trigonal pyramidal. Ignoring that, that's another bent, right? So you kind of ignore those. But I want you to be able to understand what the geometry is, what the name of the shape is, not based on these kind of my little cool, I hope you like my little drawings I spent a few years ago. I made this for my old school, these 3D drawings, but given the Lewis structures. Yes, I could ask you maybe for a quick question, I could draw that or just copy and paste that onto the final and ask you what the name of that shape is. And I hope you can recognize that that is octahedral. But more likely, I'm going to give you something like these here and ask you what the name of the shape is. So based on how many atoms are attached to the central atom, and if there are lone pairs, you should be able to identify what the name of the shape is. So let's go from this column to that column. Here, I drew them. Yeah, I could ask you that in the final. I could show you those images. But I want you to be able to know these Lewis structures, even with like real atoms, not just M's and X's. And what the name of the shape that will result from that. And again, we're going to go ahead and skip trying to understand it logically. I hope it made sense when you learned it. But just now that we have a test, let's just get the answers. So this is another thing you could write on your cheat sheet. Just draw those, literally draw those, and then put the names of the shapes. So without further ado, pretty easy. If you have a central atom with two things bonded to it and no lone pairs, that's linear. If you have three things attached to your central atom and no lone pairs, it's trigonal planar. Four things attached and no lone pairs, tetrahedral. I don't know why I'm circling. Five, oh, just to show you what I'm pointing at. Actually, do you guys see this? I like this sort of thing it does with the little laser that I can kind of point at things, but it goes away. But anyways, I'll do that. So 5 things attached and no lone pairs, trigonal bipyramidal, sorry. 6 things attached and no lone pairs, octahedral. But then the 3 that I made you responsible for, if it has 2 atoms attached and 1 lone pair, that's bent. Then there's the other bent where you have 2 things attached and 2 lone pairs. And then you have 3 atoms attached and 1 lone pair, and that's your trigonal pyramidal. So no more explanation here, just write them down if you don't already know them. And I think it made sense to you when you learned this, why those were the shapes they are. And believe me, 2 years from now or a year and a half from now when you're learning it in chemistry, it'll make more sense. You're going to forget this, but it'll come back to you in the recesses of your mind. You'll go, oh yeah, that's right. That's what it is. So this is actually a polarity and IMF review sheet. But let's go ahead and practice this skill that I was talking about. In this top half, let's first practice naming the shape it'll have. So that top one, top left, what is that going to be? That's going to be your trigonal pyramidal. Okay, 3 atoms attached and 1 lone pair. That's what I'm talking about. You should be ready for that. What about the second one? It has 2 atoms attached and 1 lone pair. That's going to be bent. Third one, that's the trigonal planar one, because it has 3 atoms attached and no lone pairs. You see what I mean? This is what I want you to get good at. This is, again, I won't rewrite it. This is the same as over here, trigonal pyramidal. We're going to go back and see if these are polar or not. This is linear because there are 2 atoms attached and no lone pairs on the central atom. That's tetrahedral, 4 atoms attached and no lone pairs. Trigonal bipyramidal, 5 atoms attached, no lone pairs. There's our other bent shape that has 2 atoms attached and 2 lone pairs. Then we have another trigonal bipyramidal, an octahedral, another bent, another trigonal planar, another bent, another tetrahedral. So be able to identify the names of those shapes based on the, just kind of erase this down, based on the Lewis diagrams. Of course, we can say the same down here, and I'll just show you the answer key later. But now as far as identifying if they're polar or not, that's what I was saying up here, is if it's identical terminal atoms and one of the shapes that doesn't have a lone pair on the central atom, it's non-polar. Those are our guaranteed non-polar ones. If there's a lone pair on the central atom for our class, where we only were responsible for 3 of those lone pair shapes, automatically say it's polar. If it has different terminal atoms, mostly it's going to be polar, but I'll point out an example. Maybe I'll draw one really quickly where it could turn out to be nonpolar. So let's just do these really quickly. And again, more likely I'm going to ask you the ones in this top half, whether they're polar or not. So let's identify which ones are polar or not. I'll circle the ones that are polar. So, hey, look, that one has a lone pair, the first one. Automatically say it's polar. Again, in chemistry, your sophomore year, you'll see that there are a couple of shapes that maybe can turn out to be nonpolar if it has a lone pair on the central atom. But for our class, as soon as you see a lone pair on the central atom, it's polar. So let's go ahead and do all those that are polar based on that rule. For our class, if it has a lone pair on the central atom, it's polar. There's something that's polar. There's polar. There's polar. There's polar. There's polar. See how easy that is? Okay, let's maybe I'll cross out the ones that are automatically nonpolar. So those are our shapes that don't have lone pairs on the central atom, that have identical terminal atoms. So where are we at? Right there. No lone pairs, identical terminal atoms. Not polar. Not polar. Not polar. Okay? And then, as I said for that last rule, if you have different terminal atoms, generally you're going to see that they're polar. Especially when I only give you Lewis diagrams, just assume if I'm just going to give you Lewis, if you have different terminal atoms, it's going to be polar. So different terminal atoms, different terminal atoms, different terminal atoms, okay? So all those are going to be polar. Now these down here, I'll just show you the answer key. Again, the same idea. It's less likely I'll do this. I'm trying to challenge you a little bit more by doing these. So just going to the answer key here. And I asked you to name the shapes again, but make sure you can name the shapes based on the Lewis structures too. And again, the same type of rule. So go ahead and study these, write what you need to on your cheat sheet if you have room, but do it. Now, what I was saying is I could be really tricky. And let's say that I was doing this last one here, and instead of drawing that one, which you can see is polar, what if I made that top one green? Like that. Is that polar or nonpolar? Well, that would be nonpolar. Whatever the bond polarity is here, it's going to be canceled by the bond polarity there, and then it's nonpolar overall. Unlikely I'm going to ask that because, again, we kind of did this really quickly at the end of the semester, but typically they're not too hard to see. You can't tell based on this, like if I had different terminal atoms, like if I had a Q, like right here, how do I know if those Q's are opposite each other or not? So you really can't identify that based on the Lewis diagram. That's why I said, if I give you the Lewis diagrams, assume that if I have different terminal atoms, then it's going to be polar. I would need to give you more information about the actual arrangement of all the red and green atoms to decide if it's polar or nonpolar. Okay, so that was a little bit quicker. So let's go ahead and hit this. Lots of problems, and I circled a bunch of things. So skills you need to know. Let's do naming molecules, which we identified because it's made up only of non-metal atoms, nitrogen and iodine. I'm providing a periodic table, of course. So what you do, the rules are, you just name the two elements, always ending the second element in "ide." Always. Yeah, I know the ionic compounds, we sometimes didn't change it to "ide," but that's ionic compounds. And then you need to use one of these prefixes, which you'll write down on your cheat sheets, to say how many of each element you have. But the two special rules, you don't say mono if there's only one of the first elements. If the second element, there's only one of it, then you do say mono. And then the rule is you drop the O or the A from the Greek prefix. I think most of those are Greek. If it's oxide. So let's just do some of these. I'll write the first one, but then I'm just going to say them verbally. You can check the answer key. Do that. So that's just nitrogen. I'm not saying mononitrogen because we don't say mono for the first one. It's just the convention. And then it's going to be tri because I have 3. And then iodide, not iodine, iodine. So you do keep the 2 I's. That one, I'll just, you can save a little time. That's going to be dibromine, not dibromide. You only change the second element to ide. Dibromine, 5 is penta, like a pentagon. Dibromine pentaoxide? No, I'll go ahead and write this because I want to make sure you get that. Dibromine, not pentaoxide, but pentoxide. So we drop the A or the O from Greek prefix endings if you're going to follow it with oxide. That's going to be tetraphosphorus heptasulfide. That is oxygen, not monooxygen, but oxygen, not oxide. The first element, you don't say ide. Oxygen difluoride, dinitrogen monoxide, not monooxide. Okay, and we do write mono for the second elements. The first element, we don't write mono. And then going backwards, really easy. I don't know if I'll give you one of these. I don't want to have such a free point there. Silicon tetrachloride, we have silicon and 4 chlorides, right? Tetraphosphorus decaoxide, that's P4, that's tetraphosphorus. And deca is 10, so we do this. Now that's what I said is, weirdly, the IUPAC naming convention is you don't drop the A for deca. I have no idea why they said that. Why not decoxide? That's not that hard. I would accept either way. I think in class I just went ahead and said decoxide, but technically it's supposed to be decaoxide. Okay, we'll just skip those. I think you get the idea. Then we did this little trick question. After doing all those molecules, I probably caught a lot of you that called that calcium dichloride. Is this a molecular compound? No, that's ionic. Different naming rules. So we would just call that one calcium chloride. We don't use dis or tris or whatever for ionic compounds. So make sure you know if it's ionic or molecular. That's a metal plus a non-metal, so we use our ionic compound naming rules. All right, then we did balancing, like I said earlier. I think this really helped you guys this year compared to my last 2 years here. First, doing all the balancing and identifying types of reactions where I give you the products. And then we got into a little bit later coming up with the products ourselves. So I'm not going to do all of these, but know the difference between the different types of reactions. So synthesis reaction is when you take 2 or more different, or 2 more things, substances, and it forms one single substance from it. Okay. Technically, it doesn't have to be different chemicals. Like I could take 2 NO2s and form N2O4, and that's still synthesis. So I don't mean it has to be different chemicals, but you're forming one chemical from it. Okay. I know I don't mean to be confusing, but don't worry about it. I think the ones I'll give you will be kind of obvious like this. So how we balance is all we do is we need to make sure we have the same number of each element. So let's just pick something. There are 2 sulfurs here and there's 8 here. Sulfur, actually, the most common allotrope is S8. It forms little octagons. So we're going to need 4 to balance the sulfurs, right? And then the domino effect is now we have 4 GEs on the right, so we need to put 4 there. This is a little bit harder. That's still a synthesis. Notice how we're never going to balance it with an odd number of oxygens, 3. I'll never get 3 oxygens on the left. And even if I made 9 oxygens on the right, I'm still not going to be able to balance there. So let's even up the oxygens on the right. We'll see if this works. We might have to change that to a 4. So that gives me 6 oxygens, but 2 sulfurs. So I know I have to put 2 here to get my 2 sulfurs. Are the oxygens fixed? Yeah, I got 6 oxygens on the left. Okay, it's trial and error. Don't think that there's a definite technique for all these types. Now, decomposition is when you take a single. Oh, before I do that, again, let me say something else. When I say that in synthesis, you're forming one product, I don't mean the coefficient has to be a 1 for the product. It's just that we have one chemical. We don't have a GES2 plus some other chemical. So the same thing with decomposition. I could have more than one of those, but decomposition is when you have one substance breaking apart into multiple things. It's fragmenting. Think of decomposition as fragmentation reaction. That's actually a pretty good name. I like that. So again, I'll just do one of these maybe. I don't know, I could do more than one. So I don't know where to start. The whole even odd thing I always like to do. So I have a 5 and a 2. Let's see what happens if I put a 5 and a 2 here. That gives me 10 oxygens. Well, now to balance it, what do I need in front of the V, the vanadium? A 4. Okay. But anyways, I'll just save a little time because I think I'm going to do some more of these decompositions later when you have to predict the products or something. So just as a reminder for 14, if I say X is combusting, that means it's reacting with O2. That's what combustion means. But what we practice a lot is combustion of a hydrocarbon. So when you combust a hydrocarbon, such as C5H12, we won't balance it here, that means we're reacting with O2, and the products, you need to memorize this or write it down, are CO2 and H2O. Okay, I'm losing my voice pretty early here. Let's see if I can hold off. I will balance it later, but know that fact that when we combust a hydrocarbon, this is what the equation looks like. Anyways, so let's actually do one here. And again, we're at this point where I'm providing it for you. So I won't explain all this. I kind of led you through this. So let's just do it ourselves. So I remember I said use the idea of CHO. Let's balance carbons first. So I did the more challenging one here. We're going to have to double at the end. So that has 4 carbons. So we need to put a 4 there, right? Do H's next. I have 10 hydrogens. So what do I need in front of the H2O? A 5. And then we do our oxygens last. How many oxygens do I have in the products? There are 8 here, plus 5 more here. That's 13 oxygens. So what fraction could I put in front of the O2 to give me 13 oxygens? 13 halves, right? That gives me 13 oxygens. But we always want fractional coefficients. I'm sorry, we don't want fractional coefficients. So we're just going to double everything. So this becomes 2, that becomes 13, that becomes 8, and that becomes 10. Okay? Pretty simple, right? 76. You're going to see I'm skipping a lot because I just gave you lots of practice. I don't know if I'll ask you a question like this, but just to make sure you understand how to name molecules, what's wrong with this one? We didn't say mono, and we didn't say di. That's dihydrogen monosulfide. What's wrong with that one? We're not supposed to say tetraoxide. What about the C? Right there. I'm going to change it to I, not chlorine. 5. Here, what kind of reaction, first of all, is this? Well, I see one chemical fragmenting, so that's a decomposition. And let's go ahead and balance it. Again, I always look for like even odd things. So I don't know if this will fix it, but let me put a 3 here and a 2 there. That at least gives me 6 oxygens, so the oxygens are balanced. But now I have 2 Ks and 2 Cls. Oh, I'll put a 2 there and it's balanced. I'll skip 6. We just did. We'll do some more later. So single replacement reactions, be able to identify it as single replacements. And the general form is you have a compound. And for this class, I'm just going to do ionic compounds. And for this class, I'm only going to have it reacting with the metals, not nonmetals. So you're looking for a compound reacting with a single element, not a compound. And what happens, remember, is the metal is going to knock off the metal. And now that metal is going to be by itself. And the metal that was by itself is now with the compound. It's the whole thing about stealing someone else's girlfriend, that type of thing, right? So zinc is hotter than silver and stole nitrates away from silver. Okay, so recognize that. Now, as far as balancing, these are typically not too hard. So don't balance nitrogens and oxygens separately. Balance the nitrates. This side has 2 nitrates. So to ever balance the nitrates, we need a 2 there. But the domino effect is, now that we put a 2 there, we're going to need 2 silvers, right? Now, how about the zincs? Are they okay? Yeah, it's balanced. Okay, let's go ahead and balance this one. Again, providing the products for you. Let's balance the chlorines, the old even-odd trick. Let's put a 3 there and a 2 there. That gives me 6 chlorines. But now I have 3 irons, so I better put a 3 there. And I have 2 aluminums, I put a 2 there. Hopefully in retrospect, you're thinking, wow, that was easy. Why did I ever struggle with those? And then finally, double replacement reactions, the 5th type that we learned. The general form is you have a compound with a compound forming a compound and a compound. And all that's happening is the metal is going to, from one compound, is going to, quote unquote, attach itself to the non-metal of the other, and that metal will be with that non-metal or that anion. So the cation of one is going to be with the anion of the other and vice versa. So that's what you saw here. It's like switching partners. You're at a dance and you switch partners with someone for a dance. So now the lead is with the chlorine and the sodium is with the nitrates. And again, later on, the harder thing is to come up with the products yourself. Initially, we were just balancing them. So I'll deal with that later. So let's just balance it now and I'll deal with how we got the products later. So again, find something. I noticed, for example, this has 1 chlorine, but that has 2 chlorines. So I better put a 2 here. Maybe that will work. But domino effect, if I put 2 in front, I have 2 sodiums. So I better put a 2 there. But domino effect, that gives me 2 nitrates. Oh, and there are 2 nitrates. And my leads are balanced. Great. Let's do one more of these. Double replacements. This has 2 hydroxide, that has 3. The old even odd trick. Okay, 2 aluminums, I better put a 2 here. 3 bariums, I better put a 3 here. Is everything balanced? Yep. Easy, right? All right, we're zooming through these. Lots of practice. So even though I went over these, let's identify the types of reactions based on what's happening. So notice this is compound plus compound going to compound plus compound. That's the double replacement, the Diara-Vila reaction. This is something reacting with O2, so that is combustion. And notice that since we're combusting a hydrocarbon, we're getting CO2 and H2O. We'll get to that a little bit later. This involves a single chemical going to 2 or more, so it's fragmenting. That's your decomposition. This involves a compound plus an element, forming an element plus a compound. That's your single replacement. And this is 2 ways we can classify that. The way I'll do it here is I'm taking 2 things and making 1 thing out of it. That would be synthesis. But how else could that be classified? Well, since it's reacting with O2, I could also call that combustion. But notice I don't have CO2 and H2O in my products because I'm not combusting a hydrocarbon. Okay, I think that's it for 77. Again, plenty of practice if you want to go back and do those yourself. I'm not going to do all of these, but let's do some of these. I probably will give you a question like this. And again, you can't balance it. It's a multiple choice. But the classic way of me of saying how to balance it is you have to balance it. But I'll just ask, when it's balanced, what is the sum of all the coefficients? We'll practice that skill. Okay, so if I said sodium, lithium, and you don't have to write the physical states. I did here just for practice. So we're saying lithium reacts with gold 3 chloride. That's going back to an old skill. I won't re-explain this. Well, I will. Gold 3 means Au3+. And what's the charge of chloride always? -1. So what's the formula? AuCl3, right? And it says it produces lithium chloride. Who cares that it's aqueous? And that's the formula, because lithium is +1, chloride is -1, and solid gold. What kind of reaction is that? Single replacement, right? So how do we balance it? Well, notice I have 3 chlorines. Let me balance the chlorines. Domino effect. I have 3 lithiums. Put a 3 in front. Let's do some more for practice. Naphthalene reacts with oxygen gas to produce, hey, guess what? CO2 and H2O. Why not? We'll go ahead and balance it. Do carbons first. Do hydrogen second. 4, not 8 there, because we're multiplying by 2. And now oxygens. I have 24 oxygens, so I need a 12 there. When oxygen difluoride gas is heated, we'll do all of these, why not? There's oxygen difluoride. It yields oxygen gas and fluorine gas. Is that right? Nope. Brinkelhoff. Don't mess this up. So let's fix the oxygens. I better put a 2 here, and I better put a 2 there. So actually, let me go back and do what I was saying before. On the multiple choice, I might say, when it's properly balanced, what is the sum of the coefficients? Don't forget that no number in front is like a 1. So what's the sum of the coefficients for this one? 3, 4, 7, 8, right? What about B? 13, 23, 27. What about C? Did I do that right? Yeah. 2, 3, 5. So include those ones. That's how I'm going to ask you to balance them. Lithium carbonate. Lithium is +1. Carbonate is 2-. So it's lithium. That's a 2 there. Carbonate. Reacts with barium chloride. Barium is 2+. Chloride is -1. All right. To form lithium chloride, I'll just go ahead and write them, and barium carbonate. So you have to figure out the formulas. Now let's balance it. I don't know, let's take care of the lithiums. I better put a 2 here to balance the lithiums. 2 chlorines. Well, we do have 2 chlorines. Hey, wait a minute, it's balanced. Okay. The sum of the coefficients, 5. Nitrogen gas reacts with hydrogen gas to produce ammonia. Is that right? No. Brinkelhoff. Okay. So we're going to need a 3 here and a 2 there. Sum of coefficients, 6. Okay. Let's go to 79. Anything here? Again, lots of repeats. So then we got to stoichiometry without limiting reactants. So just again, a brief little lesson. This says the coefficients are telling us if we take 4 moles of iron, it needs to react with 3 moles of oxygen, and it'll produce exactly 2 moles of Fe2O3, iron 3 oxide. So let's do it kind of logically without, and in sophomore chemistry, you'll use conversion factors, but let's just do it logically so you understand the process. So now we're going to say 8 moles of this react, okay? How many moles of Fe2O3 will be produced? Well, notice the balanced equation. It says for every 4 moles of iron, you produce 2 moles of Fe2O3. In other words, you produce half as many moles of Fe2O3 as you use of iron. It's a 2-to-1 ratio. So we're going to produce 4 moles of Fe2O3. I hope that makes sense. And if we react 8 moles of iron, how many moles of O2 will react with it? Well, notice that we react 3/4 as many O2s as we react of Fe. So we're going to use 6 moles of O2. Now, a way a lot of people do this, which isn't always the best, is notice that we're reacting 8 moles, which is 2 times bigger than the coefficient, right? So we're going to need 2 times more O2 than the coefficient. Again, not always the best way to think about it, but it'll get you by. Let's reverse the problem. Let me go ahead and erase this so we don't get confused. Part C. Let's say that we want to produce 10 moles of Fe2O3. Well, it helps by writing it right there, right? How many moles of iron must have reacted? And again, the way that a lot of people will do this is notice that's 5 times bigger than the coefficient. So we're going to need 5 times more than the coefficient, or 20 moles of iron. Okay? And how many moles of O2 must have reacted? Well, 5 times as many, or 15 moles. Okay, I hope that makes sense. Let's try, oh, that's it. Yeah, we go through 92 here, but again, we're going to skip a lot. So lots of practice, all this stuff, more practice. So then we started moving into predicting the products and then balancing it. So these got trickier. So here are synthesis reactions. I told you that if I do a synthesis between a metal and a nonmetal, we could predict the formula of the product. Now the idea is, it's just like one of those old questions from, I think, the second unit, where I said, what is the chemical formula of the ionic compound formed between such and such metal and such nonmetal? Well, we know the charges have to balance. So we're going to have aluminum forming the aluminum 3 plus ion. And what ion does fluorine like to form? F minus. By the way, notice I'm using diatomic here. F minus. So what's going to be the formula formed for that ionic compound? AlF3. Okay, it's a 3 there. So now we just need to balance it. The old even-odd trick. 3, 2, right? And then domino effect, put a 2 there. Okay, let's do a couple more. We're predicting the product first for this synthesis reaction. It's going to form an ionic compound between that metal and that nonmetal. So calcium likes to form 2 plus, oxygen likes to form 2 minus. So that's just going to be CaO, right? And then to balance it, we're going to need a 2 to get my oxygens balanced. And then we need a 2 here. Here, since we didn't really memorize this one, what's going to be the formula? Well, magnesium likes to form 2 plus. It's an alkaline earth metal. That forms 3 minus. So the formula is going to be Mg3N2. Then all we need is 3 there, and we're balanced. Okay. Now, this is what I was talking about earlier. Oh, didn't subscript that one. I expect you to know that if I say you're combusting a hydrocarbon, you know the other chemicals, right? And then we balance it with CHO. So let's practice this. If I'm combusting C7H16, what's the other reactant? Not O, but O2. That's combustion. And since I'm combusting a hydrocarbon, we're forming CO2 and H2O. It doesn't have to be in that order, but that's how I always do it. So then we use our CHO. To balance the carbons, we put a 7 there. To balance the hydrogens, we put an 8 there. I have 14 oxygens here, 8 oxygens there. That's 22, so I need an 11. Know how to do that. What's the sum of the coefficients? 12, 19, 27. Okay. Then we learned about single replacement reactions, and we started using the activity series. I could ask a quick little activity series question on this, whether a single replacement reaction happens or not. So remember, a single replacement reaction is when you react a single, for our class, just a metal atom, with an ionic compound. So what you want to do is see if Mg can replace Cu. If this single atom is more powerful, more active than the atom that's part of the compound, it will react. So let's find magnesium and copper in this activity series. There's magnesium, there's copper. Is magnesium more powerful? Is it more active? Yes. So magnesium will succeed in knocking off the copper. That's not really what it's doing, but it'll replace the copper. What about calcium and gold? Well, here's calcium, here's gold. Yes. Of course, this is going to be no, right? Can iron knock off magnesium? Here's iron, here's magnesium. Nope. Okay. Now, here's one I led you through. This is when we're first starting to balance single replacement reactions where I don't give you the products. I want you to find the products yourself. So I walked you through this one. So let's go ahead and do part B. We'll just skip to part B for this one because I kind of gave you a lot there. So how you do this, I'm just doing my watch here a second. Okay, is if I give you this, I say, write a single replacement reaction between calcium and gold 3 nitrate. What we first do is we check to see if it will happen according to your activity series. So can calcium replace gold? Yeah, remember gold is like the worst of the ones that I give you. So what you first need to do is come up with the products first. Don't start balancing yet. So what is going to be happen is the calcium is going to knock off the gold, and the gold will be by itself. And now the calcium is going to be partnered with the nitrates. And what I did is I just said, let's just partner them together. Calcium is going to form 2+, right? And it's going to be partnered with nitrate, which is -1. Now, what's going to be the chemical formula between the calcium 2+ and the nitrate 1-? CaNO3 2. And then we have our gold. And now we just balance it. I didn't need to really rewrite it, but I'll go ahead. And so let's balance the nitrates, the old even odd trick. And now the domino effect. And you're done. Okay, so that's the moral of the story for single replacements. See if it reacts. Just don't be in a hurry. Think about what the charges are of the new partnership and get the right chemical formula before you add coefficients in balancing it. I'm sure there's going to be more that we'll do here. 81. Okay, just a couple on this sheet. Then we learned a little bit about thermodynamics. So let's just go ahead and do this. We'll skip to the answer here. The type of potential energy stored by chemicals in their bonds is known as chemical potential energy, or CPE. Sometimes she's called chemical energy. And yes, in sophomore chemistry, this is going to be a much deeper subject. We'll end up calling that CPE pretty equivalently enthalpy. And then we learned about some properties of endothermic versus exothermic. So if you feel heat being given off, that's exo. If it feels like it's taking heat away from you, it's getting colder, that's endo. It's giving off heat to the surroundings. It absorbs heat from the surroundings. The products have less CPE. That means it's exo. It's turning CPE into heat. If the products have more CPE, meaning it's taking heat and turning it into CPE, that's endo. We'll do another one like this later. Again, feel free to pause and listen to me again. All right, let's again jump to the next one. Let's do a double replacement. And again, the first part, I led you through it. But this is very similar to what you do for the single replacements. Just take your time. There is no activity series for double replacement reactions, but technically you would say no reaction if a precipitate doesn't form, if it's a precipitation reaction. Just assume that it is reacting. I wouldn't ask you one on the final if you're going to say no reaction. So what do? We switch partners. The molybdenum is going to be now with the carbonates, and the lithium is now going to be with the bromine. So let's just first partner them up. So what is going to be the partner between the lithium and the bromine? Well, the lithium is going to form +1 ion, right? And what's bromine? Br-, right? Now the molybdenum is going to be with the carbonates. But what is the charge of the molybdenum in this compound? It's one of those that could have different charges. But if each bromine is -1 and I have 6 of those, that's -6. So molybdenum must be +6 there, right? So we're going to have the molybdenum +6 partnered with the carbonates. And what's the charge of the carbonate? 2-. So do that first. Figure out the charges. And now get the right chemical formula for your products. It's going to be lithium bromide plus MoCO3, right? And I'm not going to rewrite it, but now we just balance it. So let's deal with the bromines first. I only need to put a 6 there, right? That gives me 6 bromines. But domino effect, that gives me 6 lithiums. So I better put a 3 in front here, right? But domino effect, that gives me 3 carbonates. Oh, I have 3 carbonates. And I have 1 molybdenum. I'm done. Okay, we'll do some more of those later. So in fact, let's do one right now. Let's figure out a double replacement for this. So let's first identify the charges of all these ions. Calcium's +2, chlorine's -1, sodium is +1, hydroxide is -1, not O and H, just hydroxide. So we're going to partner them up. Let's just go straight to the products. The sodium is now going to be with the chlorine. Don't carry over that 2. What is going to be the formula between Na+1 ions and Cl-1 ions? NaCl. And what's going to be the formula between calcium 2 plus ions and hydroxide -1 ions? CaOH2. So notice I didn't carry over the subscripts. And now we just balance it. We're going to need to do 2 here for the hydroxides, domino effect, 2, and then everything is balanced. Okay, we'll do more. Identifying the number of valence electrons. So, or ideas about valence electrons. They're always the outermost electrons, farthest from the nucleus, not always, but they tend to be the outermost ones. They're the ones that do get involved in bonding. They're the important electrons. And they help determine the properties of the atom. So now let's go ahead and identify. I don't have a periodic table, but the number of valence electrons an element has corresponds to what column number it is of the main group elements, not the total column number. So for example, carbon's in column 14, but it doesn't have 14 valence electrons. It's the 4th column of the main group elements. So it has 4. Fluorine's a halogen, that's 7. Aluminum, 3. Helium, 2. Sulfur, 6. Calcium, 2. Okay. So be able to identify from the periodic table how many it has. And we use that skill later when you did Lewis dot structures. Okay, we're getting there. Let's go to 83. I skipped that. So again, let's practice a little bit these ones where you have to write the products, or maybe even write the reactants and the products. So write the balance equation for the synthesis reaction between aluminum and oxygen. Aluminum. Is that right? No, Brinkelhoff. So what's going to be the chemical formula of the product formed between these? Well, we have a metal and a non-metal. They're forming an ionic compound. So remember, aluminum likes to form 3+, and oxygen likes to form 2-. So it's going to form Al2O3, right? That's the synthesis reaction. The old even odd trick. And then domino effect. Sorry to go over it that quickly, but I think it's something that you know. Okay, write a balanced equation for the combustion of C4H6. Start with C4H6. What does combustion mean? It means reacting with O2. And when we combust a hydrocarbon, what are our 2 products? CO2 and H2O. Know how to do that. CHO. Balance the carbons. Next, balance the hydrogens. Right? Didn't lose you there, did I? Now we have 8 oxygens here. We have 3 oxygens here. That's 11. What fraction can we put in front of the O2 to get 11 oxygens? 11 halves, right? But then we multiply by 2. So this becomes 2. That becomes 11. That becomes 8. That becomes 6. And then you could go back and make sure it's balanced. And again, sum up the coefficients if I ask it that way. Okay, let's do a single and double replacement reaction. Again, plenty of examples. I won't keep doing these. Make sure you can do these. So it says between lead 4 chloride, which is that, and aluminum. Let's first see if a reaction occurs. Is aluminum strong enough to kick off the lead? Well, here's aluminum. Here's lead. Yes. So let's identify the charges first. We know that chlorine is -1. So what's the charge of lead in this particular ionic compound? +4. So what's going to happen? We don't need to know that, by the way. So we're going to have the lead kicked off. Not that you have to write that second. But now the aluminum is going to be partnered with the chlorine. What charge does aluminum like to form? +3. And chlorine likes to form -1. So the formula is going to be AlCl3. Now let's balance the chlorines, even odd. 3, 4. Domino effect, 4, 3. Sum of coefficients, 14. Now, technically, I didn't say this was charge plus 3 because back when I started, that was just solid neutral aluminum. I'm just saying when it does the single replacement reaction, it'll end up as a 3 plus ion. Okay, make sure you can do those. And again, I'm probably going to ask you what's the sum of the coefficients when you do that. Or I could ask like which of these shows a balanced equation, or I could say which one is another common one. Maybe I'll do one more just to kind of say the other common way I could ask it is I give you the two reactants and I could say which of the following A, B, C, D, E shows the right products, and I can show this and this, or I can say 3 of those and 4 of those, or I can give you the wrong chemical formula. So just know how to do it. Okay, let's do a double replacement reaction. Sodium hydroxide. Sodium likes to form +1, and hydroxide is -1. So that's going to be NaOH, right? This tells me it's iron 3+, and nitrate is NO3-. So the other reactant is FeNO3, right? So let's do a double replacement reaction. I'm going to spill over to the right a little bit. So let's find the first of the charges. I guess I already wrote the charges there, but I'll just remind us. That's +3, that's -1, -1, +1. So now the sodium is going to be partnered with the nitrate. Notice I'm not carrying over this 3. The sodium only needs 1 nitrate. So that's going to be NaNO3, right? And what about between the iron 3+ and the hydroxide -1? It's going to be FeOH3, right? All right, let's balance it. Usually the balancing is pretty easy. I'm looking at the nitrates. I have 3 nitrates there, 1 nitrate there. So I better put a 3 there. Domino effect. 3 sodiums, 3 sodiums. Domino effect. 3 hydroxides. Oh, 3 hydroxides. And I have 1 iron on both sides. So it's all balanced. Sum of coefficients, 8. Let's do one more of these. Thermodynamics. Again, believe me, sophomore chemistry, you're going to go into this for weeks and weeks. So I do a reaction, and it feels really hot. That sounds like an exothermic reaction. What happened? That must mean that CPE is turning into heat. And which is happening? The reactants had more CPE, and the CPE because the CPE turned into heat. We lost some CPE when it turned into the products. Okay, enough said there. All right, let's get to the second column. So some patterns. I'll do these pretty quickly. As you go down a column in the periodic table, what happens to the atomic radius? It gets bigger. When you go left or right, the radius gets smaller. Okay, since I don't have a periodic table, I'll kind of skip that. But know how to do them because I'll provide you a periodic table. I just don't want to try to have you memorize where those are in the periodic table. Ionization energy is how much energy it takes to remove an electron from a neutral atom. A low ionization energy means it's easy to remove an electron. A high ionization energy means it's hard to remove an electron. Thus, atoms with a lower ionization energy form positive ions more easily. What about pattern for ionization energy? As you go down a column, the IE gets smaller, and as you go left to right, it gets bigger. It's the opposite trend of radius. Okay? I know I'm going quick, but I'm just highlighting things you should know. Okay, let's go to 84. Again, you're going to see we're speeding up a little bit. Then we talked about electron affinity. So electron affinity is how much a neutral atom wants to add an electron to form a negative ion. A low electron affinity means it doesn't have much affinity for electrons. It's hard to add an electron. It doesn't have an affinity for an electron. A high EA means, it loves to add an electron. In other words, atoms that have a high electron affinity form negative ions more easily. And the pattern is the same as for ionization energy. As you go down a column, the EA gets bigger, and as you go, it goes smaller. I was thinking of radius. It gets smaller. And as you go left to right, it gets bigger. 16, let's practice one more stoichiometry. Oh, this is with limiting reactants now. So a little bit of explanation here. I'll have one question on this, and maybe a follow-up question. So this says for every 1 nitrogen, I need 3 hydrogens, and it'll produce 2 ammonias. But now let's say I want to react 5 of these. Well, if I want to react 5 nitrogens, how many hydrogens would I need? I would need 15, right? But let's say I'm trying to react 5, and I'm trying to react it with 20. Yes, my voice is sounding funny now. Do I have not enough hydrogen, or do I have too much hydrogen? I have too much hydrogen, because if I'm reacting 5 of the nitrogen, I only need 15 hydrogen. So the hydrogen is the reactant in excess. I don't have enough nitrogen to react with all 20 of the hydrogen. So the nitrogen is the limiting reactant. Now here's the moral of the story. If I want to know how much ammonia I'm going to form, I use the amount of the limiting reactant. So if I'm using 5 nitrogens, and that's the limiting reactant, how many ammonias will I produce? Well, twice as many. I'll produce 10 moles of ammonia. Okay? So that's the moral of the story is you use the limiting reactant to find out how much product you'll form. Let's try another one. I'm hurrying partly again, not just to make this video a little bit shorter, but my voice is really going. So again, this balanced equation says, however many manganeses I use, that's right, manganeses, I need twice as many oxygens, right? So if I wanted to use 6 manganese, how many oxygens would I need? I would need 12, right? So let's say that I'm putting in my container 6 moles of manganese. I would need 12 oxygens, right? But let's say I put in a container only 8 oxygens. Is that enough oxygen? No, because I said for 6 moles of manganese, I would need 12 oxygens. But I only put in 8. So that's telling me I don't have enough oxygen. So O2 is the limiting reactant. So again, we use the limiting reactant to figure out how much product will form. So since I'm using 8, so don't get confused here. I don't have 12. That was just my hypothetical amount that I would need to react with 6 moles of manganese. I'm using 8 moles of oxygen. So if I'm using 8 moles of oxygen, how many moles of manganese 4 oxide will I produce? I'll produce half as many, 4 moles of MnO4. Again, I didn't mean to confuse you by the 12. That was just my hypothetical required amount to react with 6 moles of manganese. But the real amount that I used in my container is 8 moles of oxygen. That's my limiting reactants. So I'm going to produce half as many moles of MnO4. Okay, there are more on these sheets. So let's start doing some Lewis. Again, you don't have to draw it. I'm only going to do a couple of these, but you should be able to identify what the correct drawing is. So let's do, in column A, a single atom of calcium. Well, calcium is an alkaline earth metal, so it has 2 valence electrons. So we need to put 2 dots. But the rule is you put them on different sides. It doesn't have to be left and right. It could be top and bottom, left and top, bottom and right. They just don't pair them up yet. Now, when calcium forms an ion, it forms 2+, right? It's going to lose its 2 valence electrons. So we need to draw it without its valence electrons, but you put it in brackets with the charge on the outside. Let's do phosphorus. Well, phosphorus has 5 valence electrons, so you do 1 per side until you have to pair them, and then we'll go ahead and start pairing them. Now, phosphorus, if it were going to form an ion, I'm going to guess it's going to gain 3 electrons to have an octet. So it's going to fill out its sides like this. And then because it's 3-, we're going to do that. Then we did, and we'll do another one of these later, Lewis dot structures for ionic compounds. So lithium chloride, what charge does lithium like to form? +1, right? And chlorine is -1. So what is the lithium going to look like? A lithium +1 going to look like? Well, lithium's going to lose there's lithium, neutral atom, but it's going to lose its one dot, and it's going to look like this. That is lithium +1, right? And what's chlorine going to look like? Well, chlorine, as a neutral atom, has 7 dots, but it's going to take lithium's 1 electron to get 8. So there's lithium chloride. What about calcium bromide? Well, calcium is normally this, but it's going to lose its 2 dots to form the calcium 2+ ion. Bromine normally has 7 dots, but it's going to fill out its octet and will look like that, but we have 2 bromine ions. So this is not that important. I don't know if I'll do one of these, but that's how you do ionic compounds. Not as important for Lewis structures. 85. So really quickly, let's identify the trends. For radius, going down, we have big radii. So the bottom left are the biggest radius atoms. Top right, smallest. And then IE and EA are opposites without even thinking. Down here we have the lowest IE and lowest EA. And the top right-ish, we have the highest IE and EA. And electronegativity is the same trend as IE and EA. The electronegativity would be highest in this corner and lowest in that corner. All right, let's do one more of these of ionic compounds. If we had AlF3, this is going to be Al, and I'm going to have 3 Fs. So your positive ion is always going to be devoid of dots. It's going to lose its dots, lose its valence electrons. And your negative ions are going to have gained enough dots to form an octet. Okay, enough of that silliness. So now let's get to, see, nothing there. Those are just more reviews. I didn't circle anything. Oh, down here. So now let's do pro mode. I'm skipping the first mode. And let's do the pro mode. Again, I walked you through these, but let's just jump straight to it. Let's do CHCl3. Again, you don't have to draw the Lewis structures. You just have to be able to identify if they're right or not. And one way to identify if it's right or not is A, kind of anticipate some of the trends we see for how many bonds things make, but also be careful that it has the right number of pairs of electrons. So how we did this is we add up the valence electrons. So over here, carbon has 4, hydrogen has 1, and each chlorine has 7. So that's 21, 22, 26, or 13 pairs. Okay, I added that right, 4, 1, yeah. So the first thing you do is you take your central atom and make bonds. I have 1 hydrogen and 3 chlorines. That's the first task. Second task, add lone pairs on the terminal atoms, except for hydrogen. Hydrogen does not want lone pairs. So we're at 4, we got to get to 13. 5, 6, 7, 8, 9, 10, 11, 12, 13. We're done. Now, things you should look for. Carbon, pretty much you'll always see with 8 electrons and 4 bonds. It doesn't always have to be 4 single bonds. It could be 2 double bonds, or a double bond and 2 single bonds, or a triple bond and a single bond. That's what we typically see. Hydrogen always forms a single bond with no lone pairs. And the halogens, as terminal atoms, you'll always see them with 3 lone pairs and a single bond. So everything seems to make sense. And notice my central atom has an octet, and carbon, nitrogen, oxygen, fluorine in particular follow the octet rule, so we don't need to make a double bond here. All right, let's try NHF minus. Nitrogen has 5 valence electrons, hydrogen 1, fluorine has 7, but it's a -1 ion. So do we subtract or add an electron? We add one more because being -1 means it has gained an extra electron. So 5 plus 1 plus 7 plus 1 is 14, or 7 pairs. So we said nitrogen's the central atom. We first make bonds. That's 2 of our 7. We next give our terminal atoms lone pairs to give them an octet. Hydrogen doesn't want any. So we're at 2, 3, 4, 5. We're supposed to have 12, right? So where do I put my, sorry, I was adding because I want to make sure I added that right. 5, 6, yeah, 7 pairs. So we're at 1, 2, 3, 4, 5 pairs. We got to do 2 more pairs. Where do the extras go? On the central atom. Now, check. Does our central atom have 8 electrons? Yeah. So we're okay. We don't need a double bond. In fact, hydrogen will never form a double bond. It always just forms a single bond with no lone pairs. And our halogens always just form a single bond with 3 lone pairs. But what's the last thing we need to do? Put brackets. Okay. Hopefully that makes sense. Again, you won't have to draw them, but I might give you a bunch. I might just say, which of these, I don't know how I'm going to ask it, but just know how to draw them. Okay, so I think that was it for that sheet. My fingers can't grip this to. All right, so let's go try some more. Anything on 87? No, just more practice. And I know we have some of these, but I'm going to do some more a little bit later. I can't do an infinite number of these, but look at the answer key. We've done this one before and that one, so let's do some other ones. So let's get to 88 and try some of these. Here are some patterns again, which you could write down to see, again, not all of these are always followed, but it gives you confidence that you kind of got it right. So hydrogen always wants 2 electrons. It'll have a single bond and no lone pairs. Beryllium only wants 4 electrons, 2 single bonds and no lone pairs. Boron, 6, 3 single bonds, no lone pairs. C, N, O, and F will always have 8 electrons. They follow the octet rule. Nonmetals in the 3rd period or below can have more than 8. They don't have to, but they can have more than 8. Hydrogen and fluorine always form 1 bond. Oxygen usually forms 2 bonds, but not always. You'll see times when they'll have 1. Nitrogen usually forms 3, but we saw that it just formed 2 bonds in the previous example. Often with polyatomic ions, you see them forming a different number of bonds. Carbon almost always forms 4 bonds. It's pretty strict about that, except for like we did Cn minus, it only had 3 there. Again, polyatomic ions sometimes breaks those rules. Fluorine is always a central atom. It will not want to be I'm sorry, I was thinking ahead to talk about the other halogens. Will always be a terminal atom. Hydrogen and the halogens always form single bonds. I was going to say that the other halogens could be a central atom. That's what I said here. All right, let's do BeBr2 to do a kind of one of the special rules again. So beryllium has 2 valence electrons. Each bromine has 7. It's a halogen, so that's 16 or 8 pairs. So we first make bonds to our bromines. That's 2. We got to get to 8. We now give our terminal atoms lone pairs. 3, 4, 5, 6, 7, 8. We're done with our things. Now you might say, wait a minute, my central atom doesn't have 8. Should I make a double bond? No. Remember, beryllium wants only 2 bonds and no lone pairs. So that is my answer. Okay, so don't give, and plus the halogens don't want a double bond anyways, do they? I won't do this. This will be one where it has more than 8 electrons on the central S, and it's okay. Those ones in the 3rd period or below can have more than 8. But let's do BrH3 as an example. So bromine has 7. Each hydrogen has 1. So that is 10 valence electrons or 5 pairs. So we first make our bonds. Now we have 2 pairs left over. Do I put any pairs on the hydrogens? No, they never have lone pairs. So where do I put those extra 2? Somewhere on the bromine, like that. So how many pairs, how many total electrons are on the bromine? 10 electrons, right? And that's okay. C, N, O, and F will never have more than 8. But once we get to the third period and below, it's okay if they have more than 8. They don't have to, but they can. Okay? So again, that's where we'll stop. And feel free to do the others. You're going to find out that has a triple bond, if you don't remember that. We're getting close, because again, I'm going to get a lot of repetitive things that we're going to do here, except for the VSEPR. In fact, there we go. So one way I could ask you a question, so do more Lewis if you're not comfortable with it. I could ask you the shape. I'm not going to ask you regions of electron density, and I told you I wouldn't ask you bond angle. I'm not sure why. But I could give you these 3D drawings and ask you the names of the shapes. So let's practice it. You can draw these on your sheet. That's called octahedral. I won't waste time by doing it. Pause if you need to write it down. That's tetrahedral. That's trigonal bipyramidal. That's trigonal planar. And that's linear. Okay? Here, I'm not going to do the whole thing or have you draw it, because I'm not going to have you draw it. But let's just, based on the Lewis, this is a skill I want you to have, name the shape. So what do you call it when there are 4 atoms attached and no lone pairs on the central atom? Write this down if you don't remember. I told you that earlier. That's going to be tetrahedral. So that's the rule. 4 atoms attached with no lone pairs is tetrahedral. What about 2 atoms attached and no lone pairs? That's linear. Write them down if you don't think you'll remember that. What about 6 atoms attached with no lone pairs? That's our old octahedral or square bipyramidal. What about 3 atoms attached and no lone pairs? Again, it doesn't matter that they're double bonds. There are 3 atoms attached and no lone pairs. That's the trigonal planar. Pause if you need to write that down. But again, earlier on at the beginning of this video, I showed you that little review summary sheet, and you should write that down. What about 5 atoms attached? I don't know how to draw this. And no lone pairs in the central atom. That's your trigonal bipyramidal. Okay. Then we learned about electronegativity, which is how hard each atom pulls on a shared pair of electron in a covalent bond. And the trend is the ones up towards fluorine have the highest electronegativity. So we could do this. We can say, what's the question? Which atom is going to have the bonding pair closer to itself? Well, the one with the higher electronegativity. And I might show you this, not for the values, but just to know which one has a higher electronegativity. So fluorine's always the highest, so it's going to pull the electrons closer to itself. What about between Si and H? I would not ask you that one without this table, because H is kind of an oddball. It's, again, a non-metal. It kind of belongs somewhere over here, right? So I wouldn't ask you that one. How about O and N? Well, without even looking at the value, O is going to have a higher electronegativity compared to N because it's closer to fluorine's corner. So the electron pair is going to be closer to the O. And again, I won't ask you to try to compare O and H. Although I guess you'd probably know O, being the second most electronegative atom after fluorine, is going to be, it'll be closer to O than to H. I just wouldn't expect you to know Si and H without the actual electronegativity values. So 6, are these perfectly covalent, meaning are they non-polar or are they polar? So if they're identical nonmetal atoms, we'll say they're non-polar. If they're different nonmetal atoms, we say they're non-polar. So look, different nonmetals. I forgot what we're supposed to do. Oh, box the ones that are polar, circle the ones that are non-polar. So that is non-polar. They're 2 identical bromine atoms. Non-polar, 2 identical H2. But these are 2 different nonmetals, 2 different nonmetals, 2 different nonmetals. So those are all polar covalent or polar. Okay. We'll move on. We're very close. Hang in there. I'm trying to hang in there. So here we go. These are quick little problems that you should understand just based on their formula, what the shape is. So notice that I'm saying somewhere here, all of these do not have lone pairs on them. So they're these shapes right there, our original 5 shapes. And each one of those are going to have a shape based on the number of atoms attached. So CF4, it doesn't have these don't have lone pairs on them yet. So what do you call it when it has 4 things attached? Tetrahedral. What about 3 atoms attached? Trigonal planar. 5 atoms attached. Trigonal bipyramidal. 2 atoms attached. Linear. 6 atoms attached. Octahedral. So again, it was important that I said there are no lone pairs on these. And then it's just all about how many atoms are attached. That tells you what the geometry is. So here's a question like I could ask on the final, not necessarily this exact one, but kind of just like a puzzle one like this. A molecule has a tetrahedral shape. Which one of the following could it be? Well, tetrahedral requires how many atoms attached to it? It has to have 4, right? Does that have 4 attached to the central atom? No, it has 2. That has 3 attached. But that one has 4 attached to the carbon, so that could be it. That one has 5 attached. That one has 6 attached. So I could reverse the problem. I could say CH2Cl2, I guess it's kind of like this problem here. Which geometry could it be if there are no lone pairs on the carbon? Well, it has to be tetrahedral. All right, here again, I'm not going to do the whole problem in 8s, but I just wanted to say, what's going to be the geometry based on that Lewis? Well, it has 2 atoms attached, but it has a lone pair. So that is not linear. If there were no lone pair, that would be linear. But what do you call it when you have 2 atoms attached and there is a lone pair? That's the bent. We did that at the beginning of the video, towards the beginning of the video. How about this one? There are 3 atoms attached. Hey, but there's a lone pair. So that's not going to be trigonal planar. You should know that's trigonal pyramidal, not bipyramidal, but trigonal pyramidal. Okay, so based on the Lewis diagram, you should be able to look at that and go, oh, obviously trigonal pyramidal. Right? How about 2 atoms attached and 2 lone pairs on the central atom? That's the other bent. So that's all I'm asking you to memorize for those lone pair shapes. 2 atoms attached, lone pair, bent. 2 atoms attached, 2 lone pairs, bent. 3 atoms attached, 1 lone pair, trigonal pyramidal. We're getting very close. All right, maybe I don't even have any more. Let's see. I guess I did. Let's practice a couple more Lewis, or one more Lewis. CO2, I think I have another one that we'll practice. That has 4 valence electrons. Each oxygen has 6. That is 16 electrons, or 8 pairs. The central atom I didn't tell you, but obviously it's carbon. It's the one that's by itself. Let's make our bonds. Because we haven't done many that we formed. In fact, we haven't done any with the, we need to make a double bond, so let's make sure we do at least one of these for practice. Now, with the leftover 6 pairs, let's first give lone pairs to the terminal atoms. 3, 4, 5, 6, 7. Oh, that's it. Let's box our answer and move on. No. Look at our central atom. How many does it have right now? 4 electrons. Carbon, and basically everything except for beryllium and boron will need to have at least 8 there. So remember, what we do is we take away a lone pair and we can make a double bond. Does that give the carbon 8 electrons? No. So let's do the other one. Let's get rid of a lone pair there. Oops, I didn't mean to do that. Let's get rid of the lone pair there. It doesn't have to be the one on the left, but it looks better symmetric. And do that. Now, how many electrons are around the carbon? Now we have 8. Now, technically, you could have done this. You might have asked, can I do this? Could I have taken another lone pair and make a triple bond and left this one a single bond? Yeah, that's called a resonance structure. You'll learn about that in sophomore chemistry. This is the preferred shape, but if you did that one, no problem. But I probably won't give you that one as an option. So that is the correct structure. All right, do I have another one? No, but there's another problem here. So again, really quickly, let's name the shapes here. I won't do the rest of this. What is that shape? Bent. What is that shape? Trigonal, pyramidal, and that's bent. Easy, breezy, lemon breezy, whatever it's called. Another one of these kind of simple ones. A molecule has trigonal bipyramidal shape. Which one could it be? Well, trigonal bipyramidal requires how many things attached, how many atoms attached to the central atom? 5. So it has to be that one. Now let's do another one of these for practicing making double bonds. Carbon has 4, hydrogen 1, Oxygen 6, fluorine 7. That's 18 or 9 pairs. Carbon's the central atom. Let's make our bonds. For symmetry, I'm going to put the O there. So I have 6 more to use. So we're at 3 now. Give the terminal atoms an octet, except for hydrogen, of course. So we're at 3, 4, 5, 6, 7, 8, 9. We're done. Hold your horses. Does carbon have 8? No. So what do? We're going to take a lone pair from a terminal atom and make a double bond. And now it has it. Now, why did I do oxygen? I told you fluorine just doesn't like to form double bonds. You know, in general, the halogens don't form double bonds. Oxygen is actually pretty cool about having a double bond. Okay? Let's see, is that it? I keep saying that. Oh, really quickly, again, more likely, I'm going to give you the Lewis dot diagram and ask you what its shape is. But I could ask you this, but I think those are more obvious. Like you look at that, what is that? Well, duh, octahedral. So you should still know it. And you should know this is, for example, trigonal pyramidal, not trigonal planar. Trigonal planar is when they're all in the same plane. That's bent. That's trigonal bipyramidal. That's linear. That's tetrahedral. But let's go from this column to the last column. What is that? I'll do another color, maybe make it darker so it's easier to see. So that is my trigonal bipyramidal. That is going to be one of my bents. That's going to be my octahedral. Where's octahedral? Down there. That's going to be my linear. That's going to be my trigonal planar. That's my tetrahedral, my other bent, and my trigonal pyramidal. If you can't get these, shame. That's very easy. Okay, that might actually be it. 92. Okay, I keep saying that. I just don't want to leave you guys. So let's do one last one. Maybe, hopefully last one, because I know we're about the end of problems. So let's just identify these as polar and non-polar. But first, let's name the shape for practice. That one, I won't circle them. I'll just say left or right. Well, anyways, yeah, that first one, that is trigonal pyramidal, trigonal planar, linear, bent, tetrahedral, trigonal bipyramidal, bent, trigonal planar, octahedral. Believe me, I'm not a genius, but do these for a while and they become pretty obvious. Okay, so let's identify them as polar and non-polar. And again, write down my rules. And for Lewis structures, yes, let's assume that if you see a lone pair on the central atom, it is polar, because that's what we're going to be doing for our class. For the shapes we learned, a lone pair on the central atom makes it polar. And yes, if I'm doing Lewis structures, if you see different terminal atoms, it's polar. So, hey, look, there's a lone pair, polar. Look, identical terminal atoms, no lone pair, non-polar. Look, different terminal atoms, polar. Look, lone pair, polar. Look, different terminal atoms, non-polar. I'll stop saying that, it's probably annoying the hell out of you. Identical terminal atoms, no lone pairs, non-polar. Oops, I circled, because I was trying to be funny. Sorry, polar. Yes, you caught me trying to be funny there. Non-polar, lone pairs, polar. Different terminal atoms, polar. Different terminal atoms, polar. Let's double check that I didn't screw up there. Polar. Yep. Okay. And then I could do this, but again, more likely I'll do the Lewis structure to be a little bit more challenging. Well, I won't repeat the rules, but I'll just kind of give you the answer. Non-polar, identical terminal atoms. Let's just do all the identical terminal atoms, no lone pair shapes, the original 5 shapes. We've got our tetrahedral, trigonal bipyramidal, our linear shape with identical terminal atoms, our trigonal planar shape with identical atoms, and that's it. Different terminal atoms or the lone pair shapes going to be polar. Hey, look, the bent shape, the trigonal pyramidal shape, the trigonal pyramidal shape, the bent shape, different terminal atoms. That's it, guys. And dare that be the end? It is the end. Thank you guys for listening. I'll miss you guys. See ya. Bye.